so this is our last topic, so basically our last really homework. Quadratic forms, and so we had, I'll do numbers 5 and 6 I assigned, 2x squared plus 2x2 squared minus 2x1 x2. So the one new thing, if you want, other than what we have been doing in the last couple of sessions, is that we now also need to make the matrix. So step one is we know that any quadratic form gives a symmetric matrix, and the matrix is built as follows. By 2 by 2, it's even very simple. These two are the diagonal elements. We stick to the order of the variables, right? And then this is the so-called cross term. We know that we have to evenly divide it. Okay, so for more, the next one is in 3 variables. So I'll show you how to do it. If it gets a little bit more confusing if there are more variables, but so here I guess it's very clear. So I repeat, this is half of this number because together they will form then. If you would write them, so the purpose is that we have now this, right? Oh no, not is this form where x is the tuple of x1, x2. Okay, the vector. So we have a symmetric matrix. This has to be symmetric. So step 2 is to find its characteristic equation, because now we're going to diagonalize this one. Characteristic equation. We have 2 minus lambda minus 1 minus 1, 2 minus lambda. So we put this equal to 0. That is 2 minus lambda times 2 minus lambda minus 1. So that is 4 minus 4 lambda plus lambda squared, because it's actually double product formula, minus 1. So we get lambda squared minus 4 lambda plus 3. So we factor this as lambda minus 1 and lambda minus 3. All right. 2 eigenvalues, lambda equals 1 and lambda equals 3. And so the next step is to find the eigenspaces. The eigenspace for lambda equals 1. That is, we subtract, in other words, 1 from the diagonal, so we get 1 minus 1 minus 1, 1. Okay? And so we have to reduce this matrix. That is extremely quick. R2, R2 plus R1. So this gives me 1, negative 1, 0, 0. I know this is so silly to always do this, but I see that people that don't do this on the quiz sometimes get completely confused. What are we doing here with these pivot and free variables? Whenever you have a blue pivot, and there can only be one in each row, that means that you have an equation that writes the blue pivot in terms of the green variables, the free variables. Okay? And so when we write down the solution, how do we write down the solution? Okay. So the free variables are always equal to themselves. Okay, there's only one, so there's one free variable here. What about the blue variable? Well, this is an equation that tells me that x1 minus x2 equals 0. So I see that x1 is equal to x2. So that's why I put x2 here. Again, this has to be in terms of the free variable only, the green variable only. Perhaps I should have done the previous one in another color. But anyway, so then you factor this out, and there can only be the free variable here. And there's only one. In this case, in the 2 by 2 is only in one, so you can only have this one. And that's then, and this is our basis vector. Well, we have to normalize. That's another step, an extra step that comes here, because we want the orthogonal matrix that diagonalizes this guy. So we have to do 1, 1. So the square root of 1 plus 1 is 2. Okay, and so the orthonormal basis, I'm just putting the word here one more time that you hear it, but if you say basis, it's fine. But it needs to be a unit vector, right? So the way it works, let me write it again, it's you take this norm, divide by it, the basis that you have found. So you get, right, 1 over radical 2, 1 over radical 2. Okay. So now we do the same for the eigenvalue, what was it, lambda is 3. Lambda is 3 case. Now we subtract 3 from the diagonal, we get minus 1, minus 1, minus 1, minus 1. Again, well, take our time here, R1 minus R1. So we get 1, 1, minus 1, minus 1. And then we do R2, replace that by R2 plus R1. And this gives us 1, 1, 0, 0. So the same, we have the blue pivot, that means x1 is a blue variable, is a pivot variable, and the other remaining ones, there's only one left, is x2 is a free variable. So let's rewrite this now. I'll do it a little bit. This is x1 in blue, and the other one is in green. Okay, what are they equal to? They now all be in green, right? All in the free variable. This equation tells me that x1 is equal to minus x2, and as I said, a free variable is always equal to itself. And so you factor out x2 and get minus 1. Oh, minus 1, 1. And then normalize. That means we find the norm of this guy. That is the square root of minus 1 squared, which is 1 plus 1, so the square root of 2 again. And so our basis now that we have is minus 1 over radical 2, 1 over radical 2. Okay. And so where are we now? Our P, our orthogonal matrix, is now made by putting these two basis vectors that we just found. That was 1, okay, so that was 1 over radical 2, 1 over radical 2, and the other one was minus 1 over radical 2, minus 1 over radical 2. Okay. And what about the diagonal matrix? Well, the diagonal matrix is D, and the order, of course, that we have written, this was the eigenvalue corresponding to lambda equals 1. This was the eigenvector corresponding to lambda is 3, so we have 1, 0, 0, 3. Now, what we know is that, so the way we wrote this is that if we now, I did it just opposite in the book, right? I want to keep the same notation as I did. Let me see here. Sorry. So I said, yes, so y is px. So this is the matrix that gives us the change of variables. And then with this change of variables, since we have, I'm explaining again what you have, why it's like this, okay? So we know that A is equal to P inverse dP. That's the general form of diagonalizing, but since it's an orthogonal matrix, we actually can write here P transpose dP, okay? And so we now see that if we multiply the front with the transpose of x and the back with x itself, we do the same on the other side. Okay, so you see what I did on both sides, right? So you see that what I get here is this y, and this is the transpose of y, because the transpose of a product is just the opposite order of the transposes. So what we have here is yt dy. So this is, of course, our original quadratic form, and the new quadratic form in the new variables is now given by this. But we know what this means. This is easily calculated. I'm just going over the material one more time, but you can write this right away down. You know now that this means that this becomes a coefficient of y1 squared, and this becomes a coefficient of y2 squared. And so we have now a diagonal quadratic form without cross terms. Okay, so let's do an example of a 3 by 3. I mean 3 variable. Sorry, that was number 6 or number 7. Oh, number 6, okay. So number 6, we have the, let me enlarge this bit for me. It's 5x1 squared. You have to be very careful here because we have superscripts and subscripts, right? So we don't mix them up. Plus 2x2 squared plus 4x3 squared plus 4x1 x2. Okay, so how do you build a matrix? Step 1. Let's go over this one more time. And it's perhaps now, when you have more than 2 variables, it might help to put the variables here, of course, in the same order that you put them in the row as in the columns. So now what? Okay, so this is x1 squared, so we get the coefficient 5 here. Coefficient 2 and coefficient, this is x3, x3, right? So this goes here. So where does this one go? Well, x1, x2 is this position, but it's also this position because the order in which we multiply is not important. And now we have to equally divide 4 over these two positions, so this becomes a 2 and a 2. And what about all the rest? There's nothing else here. There could have been a x1, x3 or an x2, x3, but they're not there, so it means they're all zeros. Okay, that's the matrix. And one thing, of course, is if this is not a symmetric matrix, then something went wrong. Step 2. Let's get the characteristic equation. So 5 minus lambda, 2, 0, 2, 2 minus lambda, 0, 0, 0, 4 minus lambda. Now, I like the fact that I have zeros in this last row, so I'm going to do expand row 3. I've seen once in a while somebody still thinking, oh, I can pick whatever I want and take this as the factor and the cofactor. No, you can only do this. Well, if you can do this whenever you want, but then you have to take a whole row, every element in the row, or a whole column, not just one element. Why can we only do one element here? Because the other ones are 0. That's why. Okay, so we get 4 minus lambda. That's the factor. And what's the cofactor? That is 5 minus lambda, 2, 2, 2 minus lambda. So if I multiply all this out, 4 minus lambda, then I get 5 minus lambda times 2 minus lambda minus 4. Is 4 minus lambda. Here, when you in tests are so very careful, because this is, if you make a mistake here, you get the wrong eigenvalues and nothing works. You should be able to tell. People make mistakes in quizzes, and I try to point out, look, this is why you should have known you made a mistake. Because if you, for instance, find that you have 3 pivots and no free variable, that meant you were not actually having an eigenvalue and stuff like that. Okay, so let's work this out here. That is 10 minus 5 lambda minus 2 lambda minus 5 lambda minus 2 lambda plus lambda square minus 4. So now don't expand this part because we have already a factor here. This is what we love, factors, because that's how we can find roots. Okay, so what we have here is a lambda square, then a minus 7 lambda and a plus 6, yes. And that factors as 4 minus lambda, lambda minus 1, and lambda minus 6. So I get 4 roots. This equal to 0 means that lambda equals 4. This means lambda equals 1. This lambda equals 6. Be always careful with these negatives, right? Sometimes I see people forgetting that too, and then get the minus of the wrong sign of your eigenvalue. And again, it won't work. Now, 3 eigenvalues, 3 eigenvectors, we know by the general theory that they will orthogonal. So the only thing again is we have to normalize them. Okay, so it's a bit more work now because we have to do 3. So let's start with lambda equals 4. So I subtract 4 from the diagonal. So this means here, let's one more time. So I do lambda equals 4. Also be very careful with copying. I mean, I make mistakes. So it's normal to make mistakes, but try to not to make them, right? So otherwise you get wrong answers. And again, often because if you make a mistake, you get the wrong number of free variables, and that should tell you. Okay, so lambda is 4, so we get a 1 there, a 2, a 0, a 2, a minus 2, a 0, and a 0, 0, 0. That's already promising, right? We have already 1 0 row. This is actually not determined, but a matrix. Let me go back to black. Oh, well, I have to do row operation. I'm going to do row 2 minus 2 times row 1. This pivot already there, right? So I get 1, 2, 0. So what am I doing this? Times negative 2. So I get a 0 there. Minus 4, that's minus 6, and a 0. And this is 0, which I'm not going to write anymore. And then I do row 2 divided by 1/6 of row 2. And this gives me 1, 2, 0, 0, 1, 0. Now, some of you stop here because, true, you have an echelon form and you know what the pivots are, but you're solving a system of equations, and that, to get the quick solution, to go with, do not get confused by the free and the non-free variables, you should go all the way until the reduced echelon form. In other words, here are the pivots, but the 2 on top, this last one is not supposed to be there, so we do row 1 minus 2 times row 2. And then we get 1, 0, 0, 0, 1, 0. Okay, let's look what this means. this is a pivot in the first row, there's another pivot in the second row, and the other rows are 0, so there's no pivots anymore. This means there is one free variable, x3. Okay, let's not, the blues are now, so what about x1, x2, x3? Well, let's start with x3, because a free variable is equal to itself. Now this tells me, what does this tell me? That, well, x1 is equal to 0, and this tells me x2 is equal to 0. Well, fine, that's possible. So x3, 0, 0, 1. Now, one more step, I have to normalize. That's the annoying part, that's why there are the awkward numbers incoming, the radicals and so on, but fine. This case we are actually kind of lucky, because what is the norm of this thing? That the square root of 0 squared plus 0 squared plus 1 squared, that is just 1, right? Okay, so this is the basis factor. Let me not copy it anymore. Okay, that's for lambda is 4. Then what else we have? Lambda equals 1. Lambda equals 1, so I have to now put in lambda equals 1 into my matrix. I'm going to copy my matrix again. So my matrix was 5, 2, 0, 2, 2, 0, 0, 0, 4. Okay. So I'm going to subtract 1 of the diagonals. So this is A itself, right? Let me write it, otherwise later on I might get confused. So I'm subtracting 1 from the diagonal. So this is what I get. Okay. I have to have a fraction. We know this is going to happen. So small fractions like that should not scare us. Okay, so we do row. Oh, that has to be red. No, it doesn't. We're 1/4 of row 1. That gives us the 1 that we want. 1/2, 0, 2, 1, 0. And actually, I can do also already get rid of row the 3 in there, row 3 divided by 3. Okay. I want to make this comment because sometimes people still make mistakes. When can you combine a couple of row operations at the same time? When you are not mixing rows, meaning I'm working with row 1, here I'm working with row 3. Okay, I should be a bit more precise. If I'm changing different rows. Okay, but sometimes people use row operation row 2 to change row 1 and then row 1 to change row 2. Now, if you do this simultaneously, yeah, right, and then things disappear sometimes. So that's why people sometimes get too many 0 rows. But you kind of always have to do this in order, right? So if you write this one first, that's the top one first, you do the top one first, and then the bottom one first, you do the bottom one first. So you're not really doing it simultaneously. Okay, so this is what it is. I need to make this a 0 here, so I'm going to do row 2 minus 2 times row 1. 1/2, 0, so I'm doing this minus 2, so I get a 0, that's 0, that's good news, right, because that's what I want. 1, so I don't want the 0 row, I should switch it, but I'm not, that is really not necessary to make that extra step. Now above this 1 I have a 0, and above this 1 there's nothing, so I'm in the reduced echelon form, so I'm where I want to be. So this means, okay, the pivot, x1, x3, so this time x2 is the free variable. Alright, so x1, x2, x3. What is x2 is x2, let's write that first, and then you don't get confused. And then what about x1? Well, this tells me x1 is minus 1/2 x2, and this tells me that x3 is 0. So I get x2 minus 1/2, 1, 0. And I can take, for instance, x equal to 2 to do not get an awkward fraction here, so minus 1, 2, 0. Okay, we have to normalize. And that is the norm of this guy, minus 1, 2, 0, is the radical of 1 plus 4, that's radical 5. Right? And then, so here, by example, often we find the same norm, right? But here, this is not the case, right? This had norm 1 and here norm 5. So it's just because we were dealing with very easy examples, that's why. Okay, so the last one is lambda equals 6. So I have to subtract now 6 from the diagonal. My matrix is just out of sight. Can I do it this way? Oh, it does work this way. Okay, sorry. Then I'm going to copy there. So what am I doing? Lambda equals 6. So I'm subtracting 6. I get minus 1 to 0, 0 minus 4, 0, 0, 0 minus 2. Right? That's what happens when I subtract 6. No, that's not right. Oh, the 2 here. See, you have to be very careful, because then I noticed already that this would not have free variable, because I saw the rows were kind of too different. Now I'm good. I'm good. Okay, let's go back into horizontal mode. It gives me more space there. Okay, so I have I don't have a pivot, so make it a pivot. And then also at the same time get rid of, in the third row, that number there, make it a 1 there too. So we get 1, minus 2, 0, 2, negative 4, 0, 0, 0, 1. So I'm going to do row 2, replace row 2, minus 2 times row 1. So this is 0, oh no, not that one, that's minus 2, 0. Now I get 0, 0, 0, and then 0, 0, 1 again. Same, kind of similar as before, but of course the numbers are different. So we have the free variable x3 here, and the two other ones. I hope that's... So I'm going too fast. Okay, let's do it the right way. First of all, this is the pivot, and this is the pivot. So it's better to circle them, because then you don't get confused. I was getting confusing myself. This is now the free variable. So we have x1, x2, x3. x2 is equal to itself. From this equation, I see that x1 is 2 times x2, and this equation says x3 is 0. So we get x2, 2, 1, 0. The norm to normalize is 2, 1, 0. Is the square root of 4 plus 1, the square root of 5. Oh, okay, right. I forgot to actually write down the basis vector, right? The basis vector is therefore minus 1 radical 5, 2 radical 5, 0, and here the basis vector. That's now the second time this happened that my... Why is this freezing? Sorry. No, I have to go in and out. Okay. So the basis vector now here is 2 over radical 5, 1 over radical 5, 0. Good. We can now wrap up make the conclusion. That's kind of step 4, I guess. Yeah, step 4 I call this. Step 4. The orthogonal matrix is obtained by putting these 3 basis vectors in the right order, or at least keep the same order than my eigenvalues. So this one, 0, 0, 1, that corresponds to eigenvector lambda equals 4. Okay. So let's do this at the same time. So here is D. So here is 4, and then we had 1. What was it now? 1, 0, 0 or 0, 0, 1. 0, 0, 1. The next eigenvalue was 1, and the vector was this guy here. So here a 1, and here we have a minus 1 radical 5, 2 radical 5, 0, and then the last eigenvector was 6. This is a diagonal matrix, all the rest is zeros here, and that is 2 radical 5, 1 radical 5, 0. Okay. And so we know now if we put the new variable, change of variables given by this orthogonal matrix. So x is of course here x1, x2, x3. You could write it out. So okay, let me write it out to show you what this actually means, right? First of all, this 1 over radical 5 is always annoying, so I'm going to take it out. But no, I cannot take it out, because then I have a radical 5 here, right? And this one. I have to factor out radical 5 everywhere. Okay, perhaps it's even still better than having fractions, so I'm going to do this. So that's my p, and then x is of course the tuple x1, x2, x3. So the actual transformation is 1 radical 5. The first one is minus x2, plus 2 x3, right? I'm multiplying this row with this column. The next one is 2 x2 plus x3, and the last one is radical 5 times x1. So if this is your y1, y2, y3, so here I've really written out what you have to do. Replace y1 by this expression, well, divided by radical 5, etc. And then your diagonal matrix will become 4y1 square plus y2 square plus 6y3 square. Okay? So that we have this, that this is true. Okay, this is, of course, this is what I just wrote down is just this, but it's no point in working out. You know how this with diagonal matrix what happens, right? So you know that you don't get cross terms and only these things. Okay, so that's how quadratic forms works, and so we'll do also a quiz on this one, and that's the end of the material that we'll cover, and the rest we will do reviews. So perhaps I'll say it many more times, but I'll say announce it now already. So the plan is, I mean, it's not 100% set yet, carved in stone yet, but the plan is that we will do a review on Thursday, but then next week, the last week of classes, on both days we will have a test, and we will divide the test in 2 parts. So it's if you want, call it a final, but do not make it sound so scary. I'm calling it Big Quiz 1 and Big Quiz 2. Big quiz because instead of 1 question, you're going to get 4 questions. Okay, and you get more time. I'll give you a little bit more time. But be careful. You are now used to solving problems taking your time. Most people take almost an hour to solve one quiz question because they go look up the review, they go look at the homework problems perhaps, and then they solve it. But on a test, a real test and a final test like this, or a bigger quiz where you have many questions, you don't have the luxury to go and study every topic at the moment. You should prepare yourself. Okay? Although we are now online and everything is open book, that doesn't mean that you should not prepare yourself. It doesn't mean that you just, oh, whatever the question is, I'm going to look it up. Yeah, that's going to take too much time. How many videos did we watch? Remember? This is going to take you forever to figure it out. So you have to prepare yourself by going over all the relevant videos. Now, of course, this only works for the second part. For the first part of the semester, you just have to go over the homework problems that we went through. And of course, I'm going to do a review, so you'll get the problems from there. And also the first midterm. Okay, but I'll say more about the final again, because I will write it down and make a separate video of it. But I just want to already warm you up to it, all right?